Good morning. Today we'll be talking about a very important aspect of the pericyclic reaction. This is the third phase of pericyclic reaction. We'll be talking about the important aspects of different pericyclic reactions, and we'll be starting with cyclodation reactions. The first aspect of cyclodation, important aspect of cyclodation, which we'll be discussing, is a very important aspect, and this is called the Cis Endo Rule, which is normally observed in the case of cyclodations and much more predominant in the case of Diels-Alder or 4+2pi cyclodation reactions. So let's break this up and understand the Cis Endo Rule. To start with, we'll talk about the Cis rule. In fact, this is the misnomer. This is not cis. The word should be cis-oid. So it should be a cis-oid rule or an cis rule. This we've already discussed, that if you're talking about a diene or any polyene system, that polyene system to be reactive in a cyclodation reaction should assume a cis-oid conformation. Therefore, out of the two possible conformations, the trans-oid and the cis-oid conformation, it is the cis-oid conformation which is normally more reactive. So as we read this, for a diene in a 4+2pi Diels-Alder cyclodation reaction, the reactive conformation always remains the cis-oid one. It is the cis-oid one which participates in the chemical reaction. But if you talk about the steric aspects of this thing, if we talk sterically, then we know that the stable conformation of the diene should be one in which both the electron-rich double bond should be away from one another. That is the trans-oid form. However, the more reactive conformation, as I've just told you, is the cis-oid form. Now, why does this happen? But before that, let's say if I write the diene or simple butadiene in this form, the trans-oid form can be written in this fashion, in which both the double bonds are trans across the single bond. This is the single bond, and both double bonds are trans with respect to the single bond. That's why it is called trans-oid or S-trans form. And if you rotate this bond at an angle of 180 degrees, this double bond comes to this side. That means it becomes the cis-oid form. And sterically and electronically speaking, when both pi bonds are away from one another, we can expect this kind of a system to be much more stable because the interelectronic repulsions are minimized in the trans-oid. Whereas in the case of the cis-oid form, both pi bonds are close to one another, there will be interelectronic repulsions, and this kind of a system should be electronically and sterically on both counts less stable. These two forms are rotamers with respect to one another. That means the trans-oid form can, upon rotation, get converted into the cis-oid form, and cis-oid form can in turn get converted into the trans-oid form. So if some kind of an equilibrium has to be established between them, the equilibrium should largely favor the trans-oid form because it is more stable, and very less in terms of the cis-oid form. However, as we have told, that the trans-oid form is normally more stable than the cis-oid form, and the reason this is owed to is because of the fact that if you try to react a diene in a Diels-Alder reaction in a trans-oid form, I have to then write the diene in this conformation. And we know that in the case of diene, it is the terminal lobes of the diene which are normally participating in the Diels-Alder reaction. So if the terminal lobes of the diene in the trans-oid conformation are drawn, the two p lobes are far away from one another. And if we have to bond with the dienophile, then the dienophile's p lobes, that is the terminal p lobes, would be very far away from the two p lobes or the two terminal lobes of the diene in the case of the trans-oid form. Therefore, bonding distance is not achieved when the trans-oid form of diene adds on to the dienophile in a Diels-Alder reaction. So what I'm trying to say here is that interacting lobes, that is this lobe and this lobe, the terminal lobe of diene, are far away from the bonding distance. So this and this are far away from the bonding distance, and therefore effective overlap is not possible. Therefore, to achieve an effective overlap, this trans-oid form or this sigma bond or single bond should rotate at an angle of 180 degrees so as to bring this bond ahead, that is to achieve this conformation. Once this cis-oid conformation is achieved, the two terminal lobes of the diene are now close to the two lobes of the dienophile. That means a very effective bonding overlap or bonding distance is achieved. And since this bonding distance is achieved in the case of cis-oid form or the cis form, therefore we say that it is the cis rule, that is the dienes add in a cis-oid form. Now, as you know, as of what I've said right now, I'll repeat again that the interacting lobes are at bonding distance to one another. Therefore, effective overlap is possible. And since effective overlap is possible, the molecule will be forced into this kind of a conformation. Hence, a diene adds in a cis-oid conformation, and this is called the cis rule of diene in the case of cycloadditions, and more so in the case of Diels-Alder cycloaddition reaction. So this is the cis rule or the cis-oid rule in the case of dienes. Now we'll talk about the second aspect of this rule called the endo rule. Cis rule and endo rule. As far as the endo rule is concerned, we'll discuss the endo rule in such a way that while considering an unsymmetrical dienophile, we know Diels-Alder reaction consists of two reactants. One is a diene, which is a 4-pi component, and another one is a dienophile, which is a 2-pi component. Now, if a dienophile is unsymmetrical would mean that on the 2 carbon atoms of the pi bond, of the bond which is forming a double bond, one carbon atom is having different substituent than the other, then that kind of a dienophile should be called as an unsymmetrical dienophile. So if we have an unsymmetrical dienophile, the substituents on the dienophile can occupy two different spatial orientations with respect to the diene. And once that orientation is assumed, what orientation would be more stable and which orientation would be less stable is a matter of concern. Now let's try to explain what I've just now said with the help of an example. Let's say I'm considering Diels-Alder cycloaddition reaction between a butadiene and the second component is, let's say, with a propene molecule. Now this is a propene molecule, this is a butadiene simple, this is a propene CH2, CH, CH3. Now in this propene molecule, this is still a 2-pi component. The difference is that on this carbon atom, you have 2 hydrogen atoms, whereas on this carbon atom, you have 1 methyl and 1 hydrogen. Therefore, this dienophile is an unsymmetrical dienophile, and once this is an unsymmetrical dienophile, what position this substituent, this methyl substituent will occupy with respect to this diene would decide which product will predominate and will decide whether it is an endo conformation or an exo conformation. Okay, let's try to write the product first. How do we write the product in the case of cycloaddition? This we have done numerous times. You just need to move the arrows, and once you move the arrow, you end up in the formation of a 6-membered cyclohexene ring. This methyl, because once this bond formation takes place, this carbon atom now becomes a stereocenter, and if it is a stereocenter, this methyl can either go above the plane and hydrogen will be below the plane, or the other possibility is this methyl can go below the plane and hydrogen can go above the plane. Now out of these two, which product will predominate will depend upon the orientation this methyl assumes with respect to this diene, and that is where the endo rule comes into picture. Now let's try to understand the possible orientations a diene can approach as far as the dienophile is concerned. Let's talk about the possible orientations here. Okay. Let's assume that we know that diene and dienophile, once they add on to one another, normally there's a cycloaddition or an overlap between the terminal lobes of the diene with the terminal lobes of the dienophile. That means the dienophile can either approach the diene from the lower face or it can approach the diene from its upper face. Now there are two faces in which the diene presents to the incoming dienophile, either the lower face or the upper face. Let's do this assumption, or let's study this orientation one by one. Let's first talk about the case in which the dienophile, that is your propene molecule, approaches the diene from the lower face. Now this is diene. Diene is presenting two faces, either the upper face or the lower face. Either these lobes can add, or this terminal lobes either the terminal lobes lower face can add, then dienophile is adding from the lower face. Either diene's upper face can add, then we say dienophile is approaching from the upper face. The first assumption is, let's say the dienophile approaches from the lower face. Okay, what possible orientations this propene molecule can assume with respect to this diene? First case, this is the C double bond C of the propene molecule, and this one is the methyl substituent. Now first orientation is, let's say first carbon atom, this is second, third and fourth. Of course first and fourth are similar and equal, so we cannot distinguish. Anyways, just for the sake of writing, let me say this is first carbon atom and this is fourth. With respect to the first carbon atom, this methyl is towards the outside, that is methyl is away from the diene. Diene is on this side, methyl is away. This is the first orientation. Second orientation is methyl still away but not attached to this carbon atom. Let me say this is fifth and sixth, At 6th carbon atom, methyl is away. Second orientation is at 5th carbon atom, methyl is away. Both orientation represents one common thing, that the substituent attached to the dienophile is away from the molecular bulk. If that is the case, we call this orientation as the exo orientation. The word exo. Exo orientation would mean if the substituent attached to the dienophile is away from the diene, then this is an exo orientation. However, the other effect, let's say orientation 3rd and 4th. In this case, you see that let's say your methyl is towards the diene side. If it is on this carbon atom is one orientation, if it is on this carbon atom is other orientation. But in both these orientations, you can find or see that in both these orientations, the methyl of the propene molecule or the dienophile is towards the diene. Therefore, the first two orientations are exo, the other two orientations are endo in nature. Methyl substitution on the dienophile away from the diene. It is away from the diene in these two orientations. Methyl substitution towards the diene in orientation 3 and 4. Therefore, we call 3-4 orientation as the endo orientation. Of course, as you can see, orientation 1 and 2 are similar as the diene is symmetric, and similarly orientation 3 and 4 are symmetric as the diene is symmetric. Therefore, I can write either orientation out of 1 and 2, I can write one representation will be sufficient, and out of 3 and 4 I can write one representation, that would be sufficient. Let's try to draw this representation with the help of orbital pictures. Let's say I'm drawing out of the two exo orientations, I'm representing one orientation in which this methyl is away from the diene, right? I know the terminal lobe of the diene in the Diels-Alder cyclonation reaction adds to the terminal lobes of the dienophile, which of course in this case is 2 only. So there will be a bond formation between this and this, a bond formation between this and this, and a pi bond will be formed between these two carbon atoms. That means this kind of a product formation will take place. If this kind of a product formation takes place, the methyl in this example is towards the right, that is away from the diene, and it cannot change its position, it cannot change its geometrical position, because earlier this was a double bond. Before the reaction, the dienophile was a double bond, and therefore methyl cannot rotate, or this carbon-carbon bond cannot rotate, and methyl cannot go from the right side, that is away from the diene, towards the left side, that is towards the diene. So it cannot rotate. And even during the course of a pericyclic reaction, as we know, pericyclic reactions are concerted. Therefore, when this bond is breaking, simultaneously this and this bond is forming. Therefore, again this bond cannot assume a single bond character, and since it cannot assume a single bond character, it cannot rotate. Therefore, whatever is the positioning of the methyl in the reactant, if we are talking about the exo conformation, it will remain again in the product also, it will remain on the same side without a change in its position, because the carbon-carbon is never permitted to rotate and change its substituent's position. Therefore, methyl, if it is on the right side in the reactant, since it's an exo conformation, it will remain towards the right only. Now, in order to draw this molecule properly, I lift this flap up. Once I lift this flap up, what will happen? Along with this flap, these two substituents will also be lifted. This methyl, once it assumes this position after lifting, this methyl will come in this position, this hydrogen will come here. On further lifting and making it a simple cyclohexene molecule, you'd see that methyl occupies the, in this particular case, this position, that is above, and hydrogen goes down. In order to represent in a three-dimensional manner, this is a cyclohexene molecule. Cyclohexene molecule, methyl is coming above the plane and hydrogen is coming below the plane. So this is the first product of the exo orientation which we have discussed. As I've told you and I've written here, methyl and hydrogen cannot change positions, as the dienophile's bond never assumes a single bond character. Therefore, the product which we obtain in this case is the exo product. Okay. Now let's talk about the second probability, that is the endo product. While writing or drawing the endo product, see how do we draw an endo product. The only difference between the exo orientation or an exo approach and the endo orientation or the endo approach is that in the endo case, the substituent on the dienophile is towards the diene. So methyl is towards the diene. Methyl on the left, diene is again on the bulk, is towards the left side, right? And once the product formation takes place, again it's a simple thing. The sigma bond has to form between the terminal lobes of the diene. These are two terminal lobes, and the terminal lobes of the dienophile, which are these two lobes. So one sigma bond here, one sigma bond here, one electron each in this orbital will undergo a sideways overlap to form a pi bond. Therefore, my product will be this one. Again, This bond never assumes a single bond character. Methyl and hydrogen cannot swap positions. Methyl will remain on the left as it was in the starting. You raise this flap, methyl will go down, hydrogen will go up. So if you write this in a cyclohexene form, simply in this form, then you can say in this product hydrogen is above the plane and methyl is below the plane. Hydrogen above the plane, methyl below the plane, and here we are indicating that this product is the endo product, right? Now let's talk about the stability or the preference of a particular conformation in this particular example. That is whether it is the endo or the exo product which will be formed in preference to the other one. Let's discuss this slowly. As I read, an exo conformation should be sterically less crowded. This is right because methyl is away from the diene. So sterically speaking, this is less sterically hindered. Therefore, an exo conformation is sterically less crowded and sterically more stable, obviously, and hence the kinetic control. Hence, this reaction will follow a kinetic control. The kinetic control of the reaction should make the reaction move in the direction of an exo transition state, and hence will lead to the formation of the exo product. So what I mean to say from here is that if you talk on the basis of steric grounds only, then probably it is the exo approach which is sterically less crowded. If it is exo approach which is sterically less crowded, molecule will at once try to assume the conformation which is sterically less crowded, and this control or this effect is the kinetic effect because it is formed earlier fast. And once it assumes the exo orientation, the product which will predominate will definitely be the exo product in comparison to the endo product. And if you talk about the endo transition state, the endo transition state should be more crowded because methyl and the molecular dienes bulk is on the same side, and therefore it is sterically less stable, and therefore this will correspond to lesser amounts of the endo product being formed. Hence, out of the two products, exo and endo, if the steric reasons are taking precedence, or if it is only the steric reasons which are controlling the reaction, probably under those conditions exo product will predominate and endo product will be only in the minor quantities. However, this is not always the case. At times it is the electronic control which is also there in certain reactions, and whenever there is an electronic control, then under those conditions the reaction would produce different results. That means whenever there is an electronic control, probably endo product will predominate over the exo product. However, up to this point, speaking on the terms of steric grounds only, it is the exo product which should predominate. Now let's talk about the second orientation. As I've told you, this was the first orientation in which I've told you that diene approaches the dienophile from the lower face, remember. Now the second orientation is, imagine that the dienophile approaches the diene from the upper face. This is the diene, this was the lower face, this is the upper face, dienophile comes from the upper face. Again, two possibilities, this methyl towards the outside, away from the diene is an exo orientation. On this carbon atom or on this carbon atom, methyls are away, so this is exo orientation. Methyl substituent on the dienophile away from diene, methyl substitution on the dienophile away from diene, so both orientations are exo orientations. However, in the case of endo, what will happen? The methyl substituent is towards the diene, the methyl substituent is towards the diene, both orientations are endo. Of course, this and this orientation is similar since the diene is symmetric. This and this orientation is similar since the diene is symmetric, so I can write one of the two and that will solve the purpose. Okay, let's try to draw the product corresponding to each orientation. Okay, let's work for the exo orientation first. If the molecule is approaching, or if the dienophile is approaching the diene from the upper face in an exo orientation or an exo approach. Now, as I've told you, both exo orientations are similar and both endo orientations are similar. Let's say it approaches the dienophile, the dienophile approaches the diene from the upper face. In an exo orientation, methyl is away from the diene. This is it. There will be a bond formation between this and this carbon atom, this and this carbon atom. So this and this sigma bond is formed, right? Once this and this sigma bond is formed, again methyl and hydrogen cannot interchange positions because this bond never assumes a single bond character, and since it never assumes a single bond character, the bond cannot rotate. Since it cannot rotate, the position of the substituent will remain the same as it is in the case of reactant. This we have told many times. Let's pull this flap down. While pulling the flap down, methyl will go down, hydrogen will go up, as you can see from here to here, and finally from here to here. You can see the methyl going down, hydrogen going up, The product which we write in this case is, in the case of cyclohexene ring, is that on this stereo center hydrogen is above and methyl is down. So this represents your exo product. Okay, now let's talk about the endo orientation. If you talk about the endo orientation, how will this be different? In the case of the endo approach or the endo orientation, as I've told you, methyl would be, in the endo conformation, the methyl is towards the diene side, and once you write the product, the bond formation will take between the terminal carbon atoms of the diene, the terminal carbon atoms of the dienophile methyl, and hydrogens are not in a position to swap their positions. They cannot do it because this bond never assumes a single bond character. So we write it like this: the product, the bond formed between here and here and here and here is this and this. Methyl is towards the left side. On bringing this flap down, methyl will remain above the plane as from here to here, and hydrogen will go down the plane. In writing it in this form, we'd write that methyl is above the plane and hydrogen is below the plane. This represents the endo product. Therefore, we can write endo and exo products and correspondingly write about their stereochemistry or the stereochemistry at the stereo center, considering which kind of an orientation the molecule assumes. And as I've told you, if there are no electronic controls in the reaction, we'll be talking about electronic controls in the next example. If there is no electronic control in the reaction and it is only the steric grounds or the steric effect which is taking precedence, then probably the reaction would follow the kinetic control, and it is the exo product under those conditions which will predominate. However, endo product would always remain in the minor quantities or in the minor amounts. If the reaction have some kind of an electronic control, some kind of a inter-electronic interactions are possible, then probably a different product ratio would be seen, as we'll do in the next example of the reaction of cyclopentadiene with, let's say, methyl acrylate. We know cyclopentadiene is this molecule. Cyclopentadiene is this molecule, CP, cyclopentadiene, and methyl acrylate is this molecule. Acrylic acid, the ester of methyl acrylate, the methyl ester of acrylic acid, so it is methyl acrylate. We talk about a 4+2 cycloaddition reaction in this case. What will happen? There will be a bond force. As you know, this bond will move here, from here to here. There will be a bond formation between this and this carbon atom. This bond will move from here to here. There will be a bond formation between this and this atom. This bond will move here, and there will be a bond formation between this and this carbon atom, resulting in the formation of a 6-membered cyclohexene ring with a flap and a methyl acrylate. Now, important thing is that this methyl acrylate can either go below the plane or it can go above the plane. One product can be major, one product can be minor. First thing which we have to look out in this case is which orientation this product corresponds to, in which the carboxymethyl group is below the plane, and which orientation this product refers to, in which the carboxymethyl group is above the plane. Now, in order to understand this thing, let's talk about the possible orientations this methyl acrylate molecule can assume with respect to the cyclopentadiene molecule. Right, we'll start with the possible orientations methyl acrylate can achieve while approaching the cyclopentadiene. The first orientation which we'll be talking about here is that if the methylene bridge, that is this one, this bridge of the cyclopentadiene is above the plane of the ring. Since it's a cyclopentadiene ring, in this cyclopentadiene ring, the methylene bridge can either be above the plane, all these 4 carbon atoms will be in plane. This methylene bridge can be either above the plane or the methylene bridge can be below the plane. If the methylene bridge of the cyclopentadiene is above the plane, and therefore the dienophile, that is methyl acrylate, can approach the diene only from the lower face. What I'm trying to say is, let's assume this orientation here. Let's assume this orientation here, this one. If you look at the cyclopentadiene molecule, this is cyclopentadiene's 4 carbon atoms which are in plane because all 4 are sp2 hybridized. This is the 5th carbon atom, the CH2, and CH2 can either be above the plane, this flap, this methylene bridge can either be above the plane or it can be below the plane. Let's consider first orientation, in which this methylene bridge is above the plane. Now, in this particular case, it is important to understand that dienophile is presented with 2 different faces of the diene. What I'm trying to say, the dienophile can either approach, as I've told you in the previous exam, from the lower face, or the dienophile can approach from the upper face. If it approaches from the upper face, this methylene group will sterically repel it and will not allow the dienophile to effectively approach these two terminal lobes from the upper face. Therefore, the possible selection of the pi face of the diene is lower face if the methylene bridge is above the plane. I'll repeat what I'm trying to say. This is the dienophile. Forget about the CH2. If there was no CH2, both upper as well as lower face was similar equivalent. So dienophile has equal chances of approaching from the lower side or from the upper side, as we have explained in the previous example. But with the introduction of a methylene bridge, two assumptions can happen. Either the methylene bridge can be above the plane or the methylene bridge can be below the plane. Let's say for one moment, if we imagine a case in which the methylene group is above the plane, then probably under this condition, the upper face is sterically blocked and the lower face is sterically free. So this would force the dienophile to approach the dienes terminal P lobes from the lower face. And since diene has two faces, one face is selected because of sterically it is free over the other face, we use the term in this case as bifacial selectivity. Bifacial selectivity. That would mean, what is bifacial selectivity? Bifacial selectivity would mean that if the dienophile is, if the diene is presenting two different faces to the dienophile, the upper face is different and the lower face is different because the two faces can have different substitutions. And if the diene is presenting different faces from the to the dienophile can select one face over the other. The face it selects for the cyclodecision reaction is the preferred face, and that face is selected. Therefore, we say that there is a pi face. The two pi faces, the lower face and the upper face, the lower pi face is selected. That means there is bifacial selectivity in the case of the dienophile's approach towards the diene. Right. Now, in this particular case, the flap is above, dienophile approaches from the lower side. Again, it is the terminal P lobes of the diene which will add to the terminal P lobes of the dienophile to form the sigma bond. So there's a sigma bond between this and this flap was above. Again, the carboxymethyl and hydrogen cannot swap positions, cannot interchange position, because this bond cannot assume a single bond character. So whatever is the position of the carboxymethyl, if this is away from the diene, this is an exo conformation. Away from the diene, an exo conformation. In the product also, this will remain towards the right only. If you lift this flap, the carboxymethyl will go up, hydrogen will come down. So carboxymethyl is above, hydrogen is down, and this flap represents the methylene is above. So one thing you can notice is that in the case of the exoduct, the methylene flap and the carboxymethyl substituents both are having a cis relationship with respect to one another. So this represents the exo product. Now let's draw the endo product. The difference between the exo and the endo product is similar approach. It approaches from the lower side because the methylene bridge is towards the upper side, but the carboxymethyl substituent is towards the diene side. If the carboxymethyl substituent is towards the diene, this substituent is towards the diene, we call this approach as the endo approach, right? The endo approach. And if it is an endo approach, again, there will be a sigma bond formation between this and this lobe, a sigma bond formation between this and this lobe. This sigma bond and this sigma bond is formed. Whatever is the position of carboxymethyl in the reactant, the same will remain here. You lift this flap up, hydrogen will go above, carboxymethyl will go down. That means you write the product, this carboxymethyl here is below the plane, hydrogen here is above the plane, this methylene flap was above the plane. So if you look at the exo product in which the methylene flap and carboxymethyls were both having a cis relationship with one another, in the case of endo product, the methylene flap and the carboxymethyl were having a trans relationship with respect to one another. This represents the endo product. This was the first case where we assumed that the methylene bridge of the cyclopentadiene is above the plane, and which leaves dienophile with the only option to approach from the lower face. We'll talk about the second possibility in which we'll say that the methylene bridge of the cyclopentadiene is below the plane, and hence the dienophile or methyl acrylate, as in this case, approaches from above the plane. Like what we are showing here. See this thing? The 4 carbon atoms of the cyclopentadiene which were sp2 hybridized doubly bonded, this is the methylene flap which is now shown to be below the plane. And since the lower face is sterically crowded, upper face is sterically free, therefore there can be a bifacial selectivity, that is the upper face will be selected over the lower face. So dienophile approaches the diene from the upper face. Bi bond, a sigma bond formation between this and this, sigma bond formation between this and this sigma bond is formed. Of course, whatever is the position of carboxymethyl, as we have represented this carboxymethyl here, the substituent here is away from the diene. This is an exo orientation. Carboxymethyl remains away from the diene towards right. You lower this flap. Once you lower this flap, what will happen? Carboxymethyl will go down. Hydrogen will be up in the product. See, how would I write? Cyclohexene. This methylene group is below the plane, so dotted lines. Carboxymethyl is below the plane, so dotted line. Therefore, again in the case of exoduct, we find that the methylene bridge and carboxymethyls are both having a cis relationship with respect to one another. And let's try to write the endo approach here. It will be very much similar. The only difference is you have 4 carbon atoms of the cyclopentadiene. Methylene is below the plane. Dienophile is forced to choose the upper face. There is a bifacial selectivity. Dienophile will form a bond between this and this carbon atom, this and this carbon atom. Carboxymethyl is towards the diene, therefore it is an endo approach. It will remain towards the left, that is towards the diene. You lower this flap, carboxymethyl goes up. Therefore, in the product, if the methylene flap is below the plane, the carboxymethyl flap is above the plane. That is, the methylene and carboxymethyl have a trans relationship with respect to one another. Therefore, we can ascertain and remember this thing, that in the case of cyclopentadiene, especially if the methylene flap, let's say, is above the plane and the substituent is below the plane, probably we are looking at an endoadduct. And if the carboxymethyl and the substituent on the carbon atom of the dienophile are both having the same or cis relationship with respect to one another, probably then we are looking at a exo product. Now let's see. Now, is there any, other than the kinetic control, other than the favorable kinetic control, that is the favorable steric control, do we have an electronic control in this reaction also? In order to understand this thing, let's talk about the stability of the product. Out of the 2 products which we have written, the exo product and the endo product in both orientations, above the plane and below the plane, let's talk about their stabilities. Now, first we'll talk about the stability on the basis of steric ground. Exo product, being sterically less crowded, should be kinetically favored over the endo product. This we've already discussed. So if there is no electronic control, definitely it is the exo product which should predominate over the endo product. However, if there is an electronic ground, now what do you mean by electronic ground? Let's try to discuss this factor here. Electronic ground or electronic factor would mean that there is a favorable means bonding. There is a bonding interaction between atomic orbitals other than the frontier orbitals of the diene and the dienophile, and this could force the molecule to assume a conformation which may be sterically grounded but electronically stabilizing, and therefore reaction would follow a more stable, more controlled thermodynamic control. I'll repeat what I've said in simpler words. We have talked about this thing, that it is the terminal lobes of the diene and the terminal lobes of the dienophile which adds on to one another to form a sigma bond. These kind of interactions are the interactions between the frontier orbitals, and these interactions, as we have discussed previously also, are called primary interactions. However, there are 2 other remaining lobes in the diene which are left, which are not involved in the sigma bond formation. And if a dienophile is substituted with another double bond, whether it is between the carbon atoms only, or either it is between heteroatoms or carbon or a heteroatom, whatever, whenever we have a dienophile which has more than one double bond and both the double bonds are conjugated, then probably the second double bond will have a definite role to play. And if the lobes of the second double bond and the lobes of the diene which are not forming the sigma bond are having some kind of a bonding interaction, then this will favor and stabilize the molecule. And if it will favor or stabilize the molecule, then molecule will probably lock itself in this kind of a conformation, which is sterically though crowded but electronically more stabilizing. If this kind of an orientation is assumed, probably then the endo orientation will take precedence over the exo orientation. To substantiate what I've said, I'll talk with an example, or we'll use the FMO approach to explain this orientation. Let's talk about the electronic control which is there in the case of the endo orientation. Electronic control in endo orientation. Now let's draw endo first of all. This is the diene. Let's say methylene flap is above the plane. The dienophile's substituent, that is the carboxymethyl, is towards the diene. This represents the endo approach. Simple. then we know there's a sigma bond formation between this and this lobe, sigma bond formation between this and this lobe. These two remaining lobes are not involved in the sigma bond formation. Now, as you can see in this particular case, in the case of methyl acrylate, this is the carbon-carbon double bond which is acting as a dienophile, as a 2pi electron component. This C double bond O is another double bond which is in conjugation. So actually I'm looking at a system in which I have a double bond here and I have a C double bond O here. This is my system. If you look at this thing, this is my system. A double bond, carbon atom, and a double bond here, and you can say these two double bonds are conjugated. Now it is the lobes on this two carbon atoms, that is the lobes on these carbon and oxygen atom, and these lobes, if they interact in a favorable way, favorable means in a bonding methodology, then probably there will be a stabilization, extra stabilization which is provided to the system. And if extra stabilization is provided to the system, then there will be a loss in energy, there will be a possibility stabilization which is provided to the molecule and which has much stronger control than the steric control, and therefore a molecule can then be locked in an endo conformation. Let's try to explain this thing with the help of the FMO approach. Okay. Now we know in the case of cyclodation reactions, the FMO approach is used or done in a way in which one component is considered as HOMO and other component is considered as LUMO. So we can take any component as HOMO, any component as LUMO. This does not change the course of the reaction conditions. We know this thing. Let's say we take cyclopentadienes HOMO and we take dienophile, that is methyl acrylates, LUMO. Now cyclopentadiene is a 4 electron system. HOMO would be Psi2, because I have to accommodate 4 electrons. First 2 will go to Psi1, the next 2 will go to Psi2. HOMO is Psi2, Psi2 has one node. How do we draw this thing? This is my cyclopentadiene. Let's say if this is negative, then one node has to come here. This will be negative, this will be positive, positive. This is the representation, the HOMO representation of the cyclopentadiene. If I am considering HOMO for cyclopentadiene, I have to consider LUMO for methyl acrylate. Now this is where the conceptuality has to come in. Normally when we say dienophile, we talk about 2 pi electrons, and when we talk about 2 pi electrons, we say there will be two molecular orbitals. One will be pi 1, another will be pi 2 star. This is what we've always been discussing about. However, when a double bond, as in this case, is in conjugation with another double bond, whether it is between carbon-carbon atoms and carbon or a heteroatom, as in this case it is a carbonyl group, then I have this double bond which is in conjugation with this one. In order to consider its HOMO or LUMO, since these two double bonds are in conjugation, I can consider this as a 4 electron system, 2 contributing from the dienophiles, 2 double bond and 2 electrons coming from the carbon oxygen bond. So this is basically a 4 electron system, and if it is a 4 electron system, because 2 double bonds are conjugated, then the LUMO should be pi 3 star m. Then if the LUMO is pi 3 star, then they should have 2 nodes. Therefore, if I am considering HOMO for one component, I have to consider LUMO for the other. LUMO is pi 3 star. Pi 3 star would mean there is 2 nodes, one here and here. If a node is here, I have purposely drawn, if I have drawn negative here, I have purposely drawn negative. With the node will be positive, with no node positive, with the node will be negative. So this is my orientation of methyl acrylate molecule in an endo orientation. See, why endo? Because this was carbon-carbon double bond, CO2 Me group, this one was towards the diene. So it is an endo orientation. Now look at this thing. Why this reaction is thermally loud? Because negative interacts with negative, positive with positive. There is a bonding interaction between the two. This interaction, which leads to the formation of a sigma bond, are called primary interactions. Now, as I've written, first of all about this thing, dienophile is a 4 electron system, 1 carbon-carbon double bond and 1 carbon oxygen bond in conjugation. Now, as far as the interaction between these lobes are considered, we call this as primary interaction, and we know these primary interactions are bonding in nature and lead to the formation of sigma bonds, 2 sigma bonds here. However, one thing which you should notice here is that these lobes and these lobes, which are not forming sigma bonds with one another, they are also in close contact with one another, though not at bonding distance, but they are still close to one another. And if they are close to one another, there can be some kind of an interaction between them. If the two lobes are close to one another and are having some kind of a bonding interaction, this kind, as in the case of this particular orbital chair, this carbon and this lobe has positive signs in close contact with one another. If the two lobes are in close contact with one another and they have similar kind of a signs, that means there will be a bonding interaction. And if they have a bonding interaction, then probably we can assume an orientation in which this kind of a conformation which is sterically crowded because this and this group are on the same side. However, it is energetically stabilizing as these two lobes are in a bonding orientation. Hence, and therefore, I can say this interaction, which we should use the word secondary interaction or the secondary orbital interaction. This is not primary because this is not forming bonds. This is a secondary interaction because it is forming or showing a favorable secondary interaction which is bonding in nature because similar signs are interacting. Since no sigma bond formation occurs, but bonding interaction stabilizes the endo approach and forces the dienophile to assume this conformation in precedence to the exo approach. Therefore, I would repeat that it is this orientation, the endo orientation's secondary orbital interaction, which forces the molecule to assume an endo orientation even though it is sterically more crowded. And that is where the second rule, first of all was the cis rule and the second one was the endo rule. That is where the second endo rule comes. Therefore, if the diene is showing a cis-oid conformation in reaction in a DA cyclodation reaction, the dienophile which is attached to an additional double bond which is conjugated with the first double bond should have an endo orientation with respect to the diene. So cis-oid or cis with respect to diene and endo conformation for the dienophile. This is the cis endo rule or the cis-oid endo rule of the dienophile. So now let's see, is the secondary orbital interaction present in the case of your exo approach? Let's try to draw the exo approach. As I've written, absence of electronic control in exo approach. Again, the cyclopentadiene molecule methylene above the plane. The dienophile is forced to come from below the plane. Since it's an exo approach, the carboxymethyl substituent is away from the diene side. Is right? Okay. Now again using the FMO, let's try to explain this thing. Again writing the FMO approach, the HOMO for this is psi 2. Since two bonds are in conjugation, the LUMO here is psi 3 as I've told you. HOMO has one node, LUMO has two nodes, so one node can be drawn positive, positive, negative, negative, with two nodes here and here, positive, negative, negative, positive. This is the orientation. Positive interacts with positive, negative with negative. There is a bonding interaction. This is primary interaction because it leads to the formation of two new sigma bonds. The secondary interaction which could have been possible between this orbital and this orbital is not possible because these two orbitals are far away from one another, not in bonding distances to one another, and since they are far away from one another, they cannot interact, and since they cannot interact, this kind of an interaction which is not there only cannot stabilize the system, and since the stabilization is not provided to the system, I can safely say that the electronic control or the secondary favorable interaction is absent in the case of exo approach. So one contrasting effect which we have seen in the case of electronic control is that exo approach does not have a favorable secondary orbital interaction, but an endo approach has a favorable secondary orbital interaction, and it is the favorable, the single word answer to the point, it is the favorable secondary orbital interaction which forces a dienophile to assume an endo orientation with respect to the diene. Therefore, and of course if you write the product can be simple, is this product. Therefore, in an exo approach, the secondary orbital interactions are absent and the conformational preference would only come from the steric effect. So whatever control is there is coming from the steric effect. Hence, in cases where favorable secondary orbital interactions are absent owing to the non-availability of a conjugated pi bond in dienophiles, the reaction proceeds to the formation of a transition state under exo orientation. What does it mean? In those examples in which the dienophile is not substituted by a double bond which is in conjugation with the double bond acting as a dienophile, then under those conditions we do not have a secondary orbital interaction either in exo or endo conformations. Then under those conditions it is the exo product, because it is sterically free, is the favored product of the two. And in all other cases means those cases in which dienophile have a conjugated pi bond, that is at least two pi bonds are there in the dienophile which are in conjugation, then it is the endo approach which is always favored due to the word used is favorable secondary orbital interaction. Favorable would mean bonding, and it is therefore the endo product which should be thermodynamic product because it deals with energy part. Therefore the endo product, even though it is sterically strained, is the preferred product. hence I can now sum it up and say that under those conditions in which you have a system in which the dienophile is attached to a double bond which is conjugated to the first double bond of the dienophile, then under those conditions the molecule would prefer an endo conformation. And if a dienophile is there which do not have a double bond, or which has a double bond which is not in conjugation with the first double bond of the dienophile, then probably it is the steric control which takes precedence, and under those conditions it is the exo product which is predominant in comparison to the endo product. So this is something regarding the example of methyl acrylate and this thing. I'll talk about the third and final example explaining the cis endo rule in the diene. Now let's talk about the third example, which is dimerization of cyclopentadiene. So that means in this particular case I have two molecules of cyclopentadiene. If there are two molecules of cyclopentadiene, one can act as a diene, another one will act as a dienophile. One will act as a 4-pi component, another will act as a 2-pi component. So if I have to write the product here, there will be a bond formation between this and this. That means a bond formation here. There will be a bond formation between this and this, a bond between this and this, and there will be a bond formation between this and this. That means a bond between this and this. So my product is something like this, right? This is 5-membered ring like this. Now again, since I have a double bond which is not involved in the reaction, this double bond can be either towards the diene or away from the diene. Therefore, two orientations are possible. One CP, cyclopentadiene, is acting as a diene, and the second cyclopentadiene is acting as a dienophile. The second double bond of the dienophile, this one which is not involved in the which is though in conjugation with the first, is not directly involved in the Diels-Alder cyclodation reaction. Therefore, it is possible that this double bond can have two orientations. Either this can be towards the diene or it can be away from the diene. If it is away from the diene, this approach or this orientation is the exo approach. If it's towards the diene, we call this approach as the endo approach. Now let's try to work out the endo approach. Let's talk about the endo approach first. Now the second double bond of the dienophile, that double bond which is not involved in the reaction, is towards the diene, the first orientation. Now how do we draw this? This is a tricky part. Not exactly tricky also, but you have to understand. One cyclopentadiene acting as a diene, that means both pi bonds are involved. So this is acting as a diene, let's say the upper one, 4-pi component acting as a diene. The second double bond here should be acting as a dienophile. This is involved in the reaction. This double bond, that is the second double bond of the cyclopentadiene, is not involved in the reaction, and as depicted in this representation, it is the second double bond which is towards the diene side, as you can see in this case. If it is towards the diene side, this orientation is the endo orientation, or this approach is the endo approach. Again, this double bond is towards the diene, this double bond is towards the diene, therefore it is an endo approach. The bond formation has to take place between these two terminal carbon atoms of the diene and these two terminal carbon atoms of the dienophile. Now let's try to figure out, is there any secondary orbital interaction present in this case? But premature, I can say that in all cases in Diels-Alder cyclodation reactions, there definitely will be a favorable secondary orbital interaction which will force a molecule to get locked in an endo conformation and therefore leading to the preferred endo product. Let's see this thing diagrammatically. 4 p lobes here, 1, 2, 3, 4. Similarly, 4 p lobes here, 1, 2, 3, 4. Right? This is how we have depicted the endo conformation, right? And as I know this thing, these are the two terminal carbon atoms of the diene. These are the two terminal carbon atoms of the diene. So the bond formation has to take place between this and this carbon atom and this carbon atom. Again, this is a 4-electron system. One is homo, one is LUMO. Let's say I take this as homo. You can take anything. Let's assume I'm taking this as homo. So if it is homo, again 4-electron system, homo will be psi 2. I will have one node. One node is depicted here. So if it is positive, this will be negative. One thing. Talking about the second component, LUMO, as I've told you, this is a dienophile which is acting as a 2-pi component, but the second double bond is in conjugation. Therefore, I'll consider this system as a 4-electron system. And if it is a 4-electron system, there will be 4 molecular orbitals possible corresponding to this, and namely again psi 1, psi 2, psi 3 star, and psi 4 star. Of course, LUMO would be psi 3 star having 2 nodes. So one node will come here, another node will come here. By default, what do? I keep the signs of this lobe same. So if it is negative, I keep this as negative. With the node will be positive, and another node will be negative. the bond formation has to take place between this and this carbon atom and this carbon atom. This interaction which we are showing are primary interactions, and primary interaction would lead to the formation of sigma bond. However, if you look at the other picture, that is the secondary interaction, then you can find that this lobe and this lobe are having same signs. Even though they are not in bonding distance, they are away from one another, still they have some kind of an interaction which can stabilize the system. Therefore, there is a presence of a favorable bonding secondary orbital interaction which locks the molecule in the endo conformation or the endo approach. Therefore, it is this interaction which forces this dienophile to have this conformation, that is double bond towards the diene, because there is a bonding interaction, because there is extra stabilization provided to the system. Much more better or stronger than the disfavored steric control. So what will happen? There will be a bond formation between this and this and this and this. This is how we depicted the bond formation. These two will form a pi bond. This pi bond is already there. So this is my exo approach. I'm sorry. This is my endo product. If I have to write the endo product in this fashion, let's pick this flap up. When I pick this flap up, this CP, this methylene bridge will go up. So as you can see, this 5-membered ring is this one. This flap is lifted up. When I lift this flap up, this hydrogens will also go up and cyclopentadiene part will go down. So my product of the endo approach can be written like this or like this, right? And it is this conformation which is preferred because there is the presence of a favorable secondary orbital interaction. Let's consider the axo approach. If you consider the axo approach in this particular case, while drawing or writing the axo approach, as I've told you, the second double bond of the dienophile which is not involved in the reaction is away from the diene. If it is away from the diene, what will happen? How do I represent this thing? Again, diene drawn like this. This cyclopentadiene is acting as a diene because 4 electrons are involved, 4 pi component diene. Let's say it is this double bond which is acting as a dienophile for the second cyclopentadienyl system. Therefore, it is acting as a 2 pi component, a dienophile. This double bond, which was the second double bond of the dienophile which is not involved in the reaction, is away from the diene. Therefore, what is this conformation or what is this approach? This is a axo approach. Now, whether there is a secondary orbital interaction possible or not, in order to see this thing, again I move towards the FMO approach in explaining this reaction. While considering the FMO approach, again I can consider one molecule as HOMO, another one as LUMO. In all the previous cases I have taken the diene as HOMO and dienophile as LUMO. You can do the other way around also. You can take LUMO for the diene and HOMO for the dienophile. This will not change the interaction between the primary orbitals and the interaction between the secondary orbitals. It will always remain bonding only. Anyways, again this is HOMO. Psi 2 have one node. So this is a node, positive, positive, negative, negative. This is the first picture of the diene. LUMO, again as I've told you, this is one double bond, the second double bond is in conjugation. Therefore I consider this system as a 4 pi system having LUMO as psi 3 star, and there are 2 nodes. One node comes here, another node comes here. Since I have to interact this with this, I'll keep positive here. With one node will be negative, this will be negative, with second node become positive. So there is a primary interaction between this and this lobe leading to the formation of first sigma bond, primary interaction between this and this leading to the formation of the second sigma bond. This primary interaction will form sigma bonds. So this is one sigma bond, this one, this is the second sigma bond, this one, this is the pi bond here, and this is the second pi bond which is formed by the sideways overlap of these two orbitals, right? Now you see in this case, this orbital is having negative sign, this orbital is having negative sign. They can interact in a bonding fashion, but the problem is they are very far from one another. They are not in a position that they can interact properly. And if they cannot interact properly, there will be no favorable secondary orbital interactions present in the case of axo orientation. The only control in the case of axo orientation is the steric control. That means the reaction will follow a kinetic pathway. Right. What will be the product? As you can see, these hydrogens in the cyclopentadiene will be on this side. If you lift this flap up, hydrogens will go down and cyclopentadiene will go up. Is it right? How do I write the product from here to here? This methylene bridge When I lift this flap up, methylene bridge will go up. Methylene bridge is shown up. When you lift this flap up, this cyclopentadiene will go up and hydrogens will go down. This product which we have written is the exo product. Hence, in the case of the endo orientation or the endo approach, it is the favorable secondary orbital interaction which forces a molecule or locks the molecule in an endo conformation. But in the case of exo orientations, the orbitals which are having bonding interactions are actually very far from one another. Therefore, there will not be any interactions. Therefore, there is an absence of a favorable secondary orbital interaction, and hence the exo approach is not favored in comparison to the endo approach whenever there is a double bond in conjugation with the double bond already present in the case of dienophiles. Hence, I can sum it up and say that it is the absence of secondary orbital interactions in the exo product which makes this approach less preferred, and the only product or the product which will be formed, and therefore the exo product is the one which will be formed in the minor amount. So this product exo will be the minor product of the two, and the endo product will be the major product of the two. So if I had to sum up this entire cis endo rule, I'd say the cis endo rule is largely applicable to cyclodicial reactions, but it is also more applicable to the Diels-Alder cyclodicial reaction. The cis or S-cis or the cis-oid rule says that the diene would be reactive in the case of the diene would be reactive in the case of cis-oid form, but will be less reactive in the case of trans-oid form, because in the trans-oid form the two interacting terminal p lobes will remain away from one another and therefore will not assume the right bonding distance to bond with the dienophile. Therefore, molecule has to rotate, go to a strained cis-oid conformation in order to react. That is the first case. The second case is that in the case of those dienophiles in which the dienophile is attached to a conjugated double bond, under those conditions it is the endo orientation which is sterically more crowded as compared to the exo orientation which is favored, and the reason for the favoring or the reason for the predominance of the endo transition state is because of the fact that we witness in the case of endo transition state, apart from the favorable primary interactions, the bonding primary interactions, there is favorable or bonding secondary orbital interaction which locks a molecule in a conformation which is sterically more crowded but energetically more stable, and that particular orientation is the one which will lead to the formation of more stable, or you can say the product in more amounts as the major product in comparison with the exo product. So this is something regarding the cis endo rule. Finally, I'll talk about the reactivity of dienes for summing up this today's lecture. If you talk about the reactivity of the dienes, having understood this thing, reactivity of dienes, I'm just talking about a topic in which I'm comparing acyclic dienes. Let's say if I have cyclopentadiene and if I compare its reactivity with cyclopentadiene, which do you think should be more reactive? Now, my straightaway answer to the problem of this problem is this is not a favored conformation a molecule should assume. The favored conformation the molecule assumes is the transoid conformation, that is this conformation in which both pi bonds are away. It is this conformation which is reactive but not favored. Therefore, if there is some kind of an equilibrium between these two concentrations or some kind of a rotation possible, more molecules, in fact 90 to 95% of the molecules will remain in this conformation, and in order to react this conformation will form, otherwise it will not form easily. However, if I lock a molecule in a conformation where this bond cannot rotate, this bond can easily rotate, form transoid form. This bond cannot rotate, molecule is already present in a cis-oid conformation. If a molecule is locked, here molecule is locked in cis-oid form. If it is locked in a cis-oid form, no energy would be required to rotate and convert. No energy would be required to rotate the molecule from a transoid form to a cis-oid form. Molecule will remain in a cis-oid form because it is locked, and since molecule will remain in a cis-oid form, it is the locked cis-oid conformations which are present in the case of cyclic dienes which makes them far more reactive components in cyclodicial reaction as compared to the acyclic dienes. So I repeat, the conformation which locks the cis-oid form because of the presence of the ring structure, this cannot rotate, molecule will remain in cis-oid form and will be reactive. If I have an acyclic diene, preferred conformation is trans-oid form. Some amount of energy is required to convert this trans-oid into cis-oid form. Molecule in cis-oid form will be far less in amounts as compared to the trans-oid form. Therefore, this would be less reactive because some amount of energy would be used to convert the trans-oid form into cis-oid form. Hence, acyclic dienes are less reactive, cyclic dienes are more reactive in nature. In the next class, we'll be talking about the second aspect of cycloaddition, important aspect of cycloaddition reaction. Thank you for watching this video.